There's an expression that we can see here, 1 plus r over n to the nt power, that is found in a whole host of formulas and applications across economics and biology, banking, and elsewhere. And so we can kind of clean up this expression a little bit by setting r and t equal to 1. If we do that, if we set those values equal to 1, then we just end up with the expression that we see here, 1 plus 1 over n to the n power. And so what we have in this expression, if we kind of think about it, is we have two competing elements. On the one hand, we have the n that is in the denominator of the fraction inside of the parentheses. And so as we plug in larger and larger values for n, the expression inside of that set of parentheses becomes smaller. So for example, if I plug in 1 for n, I have 1 plus 1 over 1. So I get 1 plus 1, which is 2. So my base is 2, and then I'm going to raise that to the first power, so I get an output of 2. Now, when I increase the value of n to 2, now I have 1 plus 1 over 2, so now I'm down to 1.5. My base is getting smaller, but I'm now going to raise that to the second power, to the nth power. So by multiplying by that number more times, I'm increasing the value. This is what I mean by we have competing factors here. As I plug in larger values for n, my base gets smaller, but then my exponent gets larger. I multiply by that smaller base more times. So if I do 1.5 to the second power, I get 2.25, still a rational number, as all of these will be. If I plug in 10, if you do this on your calculator, we can do 1 plus 1/10, so it's basically 1.1 to the 10th power. You're going to get 2.5937, and there's more digits after that. I'm just going to round off to the 10,000th place. If we plug in 100, we're now looking at 1.01, so 1 plus 1 over 100, so 1.01, 1 and 1/100th, to the 100th power. So again, you can see this pattern of the base is getting smaller, but the exponent is getting larger. So our answer creeps up now to 2.7048. So you can see that we're not growing very quickly. We jumped from 2 to 2.25 by going up from 1 to 2, but from going from 10 to 100, our rate of growth has really slowed down. If I plug in 1,000, I can tell you that we end up with 2.17169. If we plug in 10,000, we barely move the needle at all, 2.7181 if we round off to 4 places. So you can see that our rate of increase is really slowing down. So even though we're multiplying more and more times, the base is getting closer and closer to 1. So we have this competing set of factors. So in the end, if we were to just continue to increase the size of n, meaning that the base is getting closer and closer to 1, but we multiply by an ever larger number of times, we eventually approach this irrational number e. So it's an irrational number along the lines of pi that does not repeat, does not end. It keeps on going forever and ever and ever. And so this number e is used as a base. It's called the natural base. And so it is used in exponential and we'll eventually see in logarithmic equations when continuous change is occurring. So if you're looking at problems involving population growth or interest growth of a investment or something like that, we're going to use this base e in a lot of those calculations. So we're going to see how that applies in the next example here in just a moment. So we can see here we've got two different growth models that are set up for us. We have what we're going to refer to as the compound interest model. So this is not for continuous growth. And then we're going to have this continuous change model, which is assuming that the growth is continuous. So every instant we're seeing an increase. Now you can see in our expression here, we've brought back r and t. So those are no longer set equal to 1. And so instead now we've got these variables that are introduced here where r is going to represent the growth rate, so that's going to be a percentage, but we're going to change that to a decimal for this equation. And then t is brought in as being the time factor. And this will almost always be in years for us. It basically is tied to whatever the rate is of growth. And then the other variables in the problem, a is going to be whatever our new amount is, so what we're going to end up with after applying this growth rate for whatever amount of time. P is our starting amount, so whatever our initial population is, or our initial investment is, or whatever. And then n in this equation is the number of compoundings per year, meaning how many times per year are we recalculating what our new amount is. So if we're compounded monthly, then that number would be 12, meaning if the interest was being applied every month, we would have 12 as our value for n. If it was daily, it would be 365. If it was yearly, n would be 1. So n is just how many times we're basically doing a recalculation. How many times is the interest being compounded per year? The more the better, as we'll see in the example below. Now if we move to continuous change, as we see in the second example here, now we no longer have this expression 1 plus r over n to the nt. Now we've moved to replacing that expression with e. So that's the 1 plus 1 over n to the n part of the expression. But then because we're not setting r and t equal to 1 anymore, those are going to be the exponents on this base e. So we're going to have to use this e button on our calculator when we get to that problem to use that natural base. So that way it'll use the entire value rather than using some decimal approximation. But otherwise in this formula, a is still our new amount, whatever we're going to end up with after the interest rate has been applied for a particular amount of time. T is going to be our amount of time. Again, that's typically going to be in years. We don't need the compoundings variable, that n, because we've basically said we're continuously changing, we're continuously compounding. So that's taken care of by the presence of e, the natural base. And so we can use this equation in those circumstances. So let's see what impact increasing the frequency of the application of the interest, the number of compoundings per year, does for us for the same investment parameters. So we have here is an initial amount, $10,000. So that's going to be our P. It's going to be invested at a 7% interest rate. So we're going to adjust that to be a decimal, so 0.07, and then for a number of 10 years. So we want to see what change it has on our outcome if we compound the interest, if we apply the interest just once a year, so every 12 months, 4 times a year, so every 3 months, 365 times, so every day, or if we do it continuously. And so for the first 3 here, we're just going to be plugging into this compound interest model. Since we're not compounding continuously, we're going to be plugging in up there. So for this first box, for example, we're going to have A, our new amount that we're trying to calculate. It's going to be equal to 10,000 times 1 plus, now our interest rate is 0.07, divided by the number of compoundings per year. So this is divided by 1, n is 1 in this case. And then we're going to raise that to the nt power, so 1 times t. We've said 10 years here, so our exponent is going to end up being 10. So really we have 1.07 to the 10th, and then we multiply that by 10,000. If we do that on our calculator, we're going to find that our $10,000 investment is going to grow to $19,671.51. So whenever we're doing a calculation involving money like this, I want to round off to the nearest penny. So now let's see how that changes if we just increase the number of times that we apply the interest rate to 4 times per year instead of just once per year. So if we do that off to the side over here, everything's going to be the same in our formula. It's still going to be A equals, still going to be 10,000 as our initial investment, still going to be 1 plus 0.07, but now n is being increased to 4. So basically we're compounding the interest every 3 months, so 4 times per year. And then in our exponent, it's not going to be 10 anymore, it's going to be 4 times 10. So we're going to get 40 as that exponent. So again, if we push buttons on our calculator to get through that, we just have to be careful with our order of operations and using parentheses and so on. But we end up with a total of 20,000 and $15.97. So you can see it's a significant increase. And the reason is by compounding that interest more frequently, essentially our base to which that interest is being applied is growing faster. So we're ever applying the interest rate to a larger number, which means it benefits us in terms of more growth. So we're making an extra $340 or so. Now, what happens if we compound daily? So now we increase that so that we're compounding the interest every day. Well, it's not going to make that much of a difference compared to the leap that we had from 1 time per year to 4 times per year, but it still is to our benefit. So the change here now, if I go up here, so now instead of 1, I'm going to have 365 in the denominator there, and instead of 10 times 1, it's going to be 10 times 365. So again, my base, my expression inside the parentheses is getting closer and closer to being 1, because it's 1 plus this 0.07 divided by 365, but I'm multiplying by that on 3,650 times using that exponent. Then of course we multiply by the initial amount, that $10,000, and so here we end up with a total of $20,136.17. So we have made a little bit more there, about $121 more by increasing the interest, but not as much of a leap as we saw from 1 to 4. Now for the final example, this is now what if the interest was being recalculated and applied to the principal every instant. So not just every day, not every minute, not every second, but continuously. So what impact does that have? Well, now we're going to be using this continuous change model. So we're going to have A equals, P is still our initial amount, 10,000. E is this natural base, so you're going to have to use the E button on your calculator. Depending on what type of calculator you have, it may be a primary button or it may be a second function above the LN key, which we'll talk about in the future. But now R in this case is going to be our 0.07, and then times T, so T is for 10 years. So you can see there's no N in this calculation because that's taken care of by E for this continuous change model. And so if we push buttons on our calculator to generate this result, we end up with the best possible scenario of $20,137.53. So you can see not much of a change from the daily compounding, but still a slight increase, an extra $1.50 or so. So again, the idea behind this is the more times we apply the interest rate, the more frequently we apply it and recalculate what the base is to which the interest rate is being applied, that's going to increase the amount of growth that we experience. So this first one here might almost be considered like a simple interest model, whereas here now we have this continuous growth, which is a little bit more representative of what happens in reality, certainly in population growth, but also in terms of investing. But we'll explore more of this as time goes by.